And welcome to Climate Chat. I am your host, Dan Miller. And today on Climate Chat, our guest is Dr. James Hansen, perhaps one of the best known climate scientists in the world. Dr. Hansen is the former director of the NASA Goddard Institute for Space Studies, where most of NASA's climate research was done. He is now director of the Climate Science Awareness and Solutions Program at the Columbia University Earth Institute. Jim, welcome back to Climate Chat.
Yeah, good to see you, Dan.
So, Jim, in the past 2 years, you published two very long papers. The first one, I'm going to pop it up here. Let's see. Let's get the paper to be big. You published two long papers. The first one is Global Warming in the Pipeline, was published in Oxford Open Climate Change. And by the way, our Climate Chat host, Leon Simmons, was a co-author with you on that paper. The second one here, let me pull that up there, was, let's see, the Global Warming Has Accelerated, which was published early this year in the journal Environment. By the way, links to both papers are in the YouTube description for people who want to dig into them. And I've talked about these papers on our Climate Chat podcast quite a bit. But recently, you published on your website and on Substack a shorter article titled Seeing the Forest for the Trees, which was right here, in which you aimed at explaining the main conclusions of the long papers. Why did you write the shorter article?
Well, partly it's because the long articles were long. And the way I tend to look at these problems, I'm looking at it from different angles. And so it gets complicated. And perhaps the main conclusions are not so clear to everybody. But also, actually, the main thing that spurred me to write this shorter thing is the reaction in the media to those papers, especially the second paper. The editor of that journal was shocked by the ad hominem response of climate scientists who were willing to speak to the media. Things like Hansen exaggerates, makes lots of mistakes, and is not collegial. These are really crazy things. Normally that's not the kind of things that journalists do. So it was surprising, and they said, well, our analysis was too simple. it was pretty complicated, but also it was outside of the mainstream. Now, the funny thing was that none of these comments addressed the climate science in our paper, and nevertheless, those opinions were sufficient to shut down the public discussion of our paper. So the purpose of the forest article is to try to make clear the scientific basis for those two papers. And the audience that I'm really aiming at is scientists other than those several who are usually available for speaking to the media about global climate change, because I think that the wider range of scientists is more, there's a lot of scientists who are capable of looking at the broad picture, and the evaluations in the media should not be restricted to half a dozen scientists.
And by the way, did any of these scientists actually contradict the science part of your paper? Did you get any pushback on the science itself?
Oh, sure. In the sense that, the first response was, there is no global warming acceleration.
Right.
But they don't get into the science of our paper and how we reach the conclusions that we
That's what I
do.
meant.
And that's what I want to try to clarify.
That's right. So in your paper, you draw attention to the fact that your analysis differs quite a bit from the Intergovernmental Panel on Climate Change, or IPCC, sort of the UN body that looks at climate change. And so before we get into the conclusions themselves, can you tell us why your conclusions are so different from that of the IPCC?
Yeah, but first I should say that with regard to the thousands of experts who contribute to IPCC, I'm not in disagreement with most of them. You know, even their ranges, that say the experts on climate sensitivity, they actually give a very large range, which would encompass the large climate sensitivity that we conclude is actually valid. And likewise with the aerosol science, aerosol scientists give a huge range. And we conclude that the aerosol cooling effect has been underestimated by IPCC, but the value that we get is within the range that the aerosol experts would say. Our conclusion is the reason it differs is that IPCC places a inordinate emphasis on GCMs,
Global climate models.
global climate models, and of course I'm aware of that because I spent a few decades focused mainly on GCMs, and I realized that some of the mistakes that I made were because of overemphasis on GCMs. We can do better if we look at the climate system in additional ways. In particular, the history of Earth, the paleoclimate information on climate sensitivity, and also the modern observations of ongoing climate processes. And so what we have been doing is trying to put a comparable emphasis on the three different ways of looking at the system: the paleoclimate, the modern observations, and the GCMs, which are essential because the human-made climate forcing is unprecedented. So we have to have models to simulate its effect. And I think the bottom line is thou shalt not worship GCMs. We need to take a broader view of climate change.
So before we get into that, into the methods that you use to determine it, as I mentioned, there's differences between what you say and what the IPCC says, and that particularly when it comes to climate sensitivity and aerosols. And aerosols, for everyone, is sort of fine particles in the air that might be caused by a coal plant emitting sulfur or a ship emitting sulfur particles. That would be considered an aerosol. But you differ significantly on those two areas. Can you first tell us what they are, what climate sensitivity is, and how big are the differences?
Sure. Climate sensitivity usually refers to the global temperature change in response to a standard forcing, that is, an imposed perturbation of the system, an imposed radiation imbalance of the planet, energy imbalance of the planet.
Might be imposed by people in this case, right?
In particular, the standard forcing is doubled carbon dioxide, which is a forcing of 4 watts per meter squared averaged over the planet. And it refers to the eventual response after the climate has come back to equilibrium with this additional forcing. So our best estimate for climate sensitivity turns out to be 50% larger than IPCC's best estimate, where they estimate 3 degrees C for doubled carbon dioxide, and our best estimate is 4.5 degrees C.
That's a huge difference. Yeah.
Yeah, so it's a big difference, and it's related to the difference in aerosols. The greenhouse gas forcing, when you add methane and chlorofluorocarbons to carbon dioxide and nitrous oxide, is about 4 watts per meter squared. We've now reached double CO2 level, equivalent of double CO2. But we've also put aerosols in the atmosphere, and they cause a negative climate forcing, a cooling.
Yeah.
And that forcing is probably in the range from -1 to -2 watts per meter squared. So it's a big deal. There are other things that are being done, but they add up to a negligible amount. So it's really a question of the greenhouse gases and aerosols. And we conclude that the aerosol forcing is larger than IPCC estimated, and that's the reason that they get a smaller climate sensitivity, because their net forcing is larger because they have a less aerosol effect. Therefore, a small climate sensitivity is able to match the observed warming over the last century.
Right.
But now we're in the process of reducing aerosols, so we're going to feel the effect of the high sensitivity and the reducing aerosols. And that's the reason that the global warming rate has accelerated.
Right. So society is cleaning up these aerosols. It's pollution, and it's bad for your health, but it also reflects the sun away, creates clouds that reflect the sun away. And so they do two things. They're bad for your health, but they also cool the earth. But we're cleaning them up for health reasons, and that's, as you just pointed out, accelerating global warming. So you said you looked at this 3 different ways. So you looked at, and this is what your Forest for the Tree article explains, how you came about this. First, by looking at paleoclimate data, such as ice age temperatures, so history, climate change from long ago that we can determine. You also use observations of the Earth changes today for things like a radiation balance measured from satellites, so current data, and you also use global climate models, or GCMs. So let's maybe walk through it. So what's the main thing that you learned from the paleoclimate or ice age type data?
Yeah. The paleoclimate provides the least ambiguous way to assess equilibrium climate sensitivity, because you can compare equilibrium climate states, 2 of them, which have different climate forcings. And in particular, the period that we know best is the current interglacial period and the last glacial maximum. And so that was the focus at the really 50 years ago, or 40 to 50 years ago, when paleoclimate data was beginning to be available in substantial amounts. There was this large project, CLIMAP, funded by the National Science Foundation at a large number of different laboratories and universities. And the CLIMAP project estimated that the global sea surface temperature, it tried to establish the surface conditions on the whole planet, but the most important one is the sea surface temperature, because the ocean covers 70% of the planet. And once you establish the sea surface temperature, that basically establishes the global temperature, because the winds move the air over continents. And so what they estimated for SSTs led to a global temperature 3.6 degrees Celsius colder during the
During
ice
the
age.
last ice age. Yeah.
Yeah. And that, and we know the forcings, the forcing that maintained the temperature change between the ice age and the interglacial, that because we know the change in the atmospheric composition accurately from the air bubbles in the Antarctic ice core, and we know the surface albedo change from the geographical distribution of the ice sheets and the sea ice that existed during the ice age. And that implied a climate sensitivity of about 2.4 degrees for double CO2. We were suspicious about that, and you know, we had this big conference at Lamont Geophysical Observatory, which Taro Takahashi and I organized at the request of Wally Broker. But there were questions about the CliMap sea surface temperatures because they were based on the assumption that the microscopic biology in the ocean surface, the foraminifera, would live at the same temperatures that they prefer today. There are lots of different species among them. And so the approach of NSF was to assume that they would live at the same temperature they do today. But what if on millennial timescales, these species partly adapt to the temperature change? In that case, the estimated temperature would be the estimated temperature change would be underestimated. Well, finally, and we were suspicious because Dorothy Petit, who was then a graduate student at New York University, but working with us and looking at pollen data, concluded that the land temperatures during the ice age were actually colder by a factor of 2. The cooling was a factor of 2 larger than what CliMap would imply. And also the snow line on the mountains moved down twice as much as it would with the sea surface temperatures that CliMap estimated. But anyway, we couldn't persuade CliMap that they were wrong. And it wasn't until 2020 that we finally got data which gave us a better indication of what the temperature was during the last ice age. And that was Jessica Tierney, who decided to omit the biological data because there had become more proxies, more chemical proxies for sea surface temperature. So she used only those and omitted the biologic data. And she concluded that the broad LGCM, last glacial maximum, was more than 6 degrees colder rather than 3.6.
Much colder than before.
And
the previous data indicated.
And then the next year, I didn't notice her paper till the next year when her postdoc, Matt Osman, published a paper for the narrower period, 18 to 21,000 years ago, the peak of the last glacial maximum. And he found it was 7 degrees Celsius colder. So we had concluded, we'd written a paper during this Ewing Symposium period, 1982 to 1984, estimating that climate sensitivity was in the range 2.5 to 5 degrees, because the 2.5 is what you'd get from CliMap. But we modeled the the global climate using the climate boundary conditions and found that the planet was out of balance, energy balance, by more than 2 watts per meter square, and it was trying to cool off. So it was telling us that something was wrong with climate data, or else our climate model was wrong. And our climate model was a model that gave 4.2 degrees for double CO2. And we had an amplifying cloud feedback. You see, the 2.5 degrees sensitivity that was estimated based on the climate data would be consistent with a climate in which clouds are neutral, because the water vapor and sea ice feedbacks are enough to increase climate sensitivity from the 1.2 degrees, which would be the sensitivity if there were no climate feedbacks.
Right. Okay. Just from the CO2.
So the sea ice and water vapor, principally the water vapor feedback, double the sensitivity from 1.2 to 2.4. In our model, it got even higher to 4.2 degrees because clouds were providing an amplifying feedback.
Right.
And who knows? I mean, we didn't know what clouds are very hard to model. So if you remember in the Charney National Academy of Science study in 1979, he estimated that the climate sensitivity was someplace in the range 1.5 to 4.5 degrees. And he looked in particular at GCM models and found range from 2 to 4 degrees, with that range mainly due to clouds and our uncertainty in how clouds actually will behave as global climate changes. Well, okay, so the new and what's perhaps even more important than the modeling studies by Tierney and Osman is the measurements that were made of, now you have to help me with this name.
Well, I won't know the name, but.
Okay, it's the measurements of groundwater deposited during the last glacial maximum. You know, we can sample groundwater and we can tell the age of that groundwater.
Okay.
And that sorry, I can't think of his name, but it was really important study. He sampled groundwater between 45 degrees south latitude and 35 degrees north latitude. Mm-hmm. And he measured the abundances of the noble gases in this groundwater. Those noble gases are their abundances are strongly temperature dependent and established by the temperature that existed at the time the groundwater was deposited. And this showed that that the average over those latitudes on land was 6.2 degrees Celsius colder than during the Ice Age than it is now. And what we show in our first paper is that cooling is consistent with a global cooling of 6 to 7 degrees cooling.
So just to summarize, what you're saying is this new data said it was colder during the Ice Age than previously thought. We know it was about 100 parts per million less CO2 compared to pre-industrial, because we could measure it in air bubbles in ice cores. So we know the change in CO2, and we know the temperature change. And when you reverse that, going to the warmer side, the doubling CO2 from pre-industrial, you come up with the roughly 4.5 degrees of warming after the feedbacks play out. Is that sort of a good summary of it?
So the paleo, it tells us that climate sensitivity is high. It's near the upper end of the range that Charney had estimated. And
okay, so that's one way that you did it. That you
right.
estimated climate sensitivity was using ice age data, but you did it a totally different way as well. You looked at satellite data of the Earth radiation balance, how much energy is coming into the Earth, how much energy is coming away from the Earth. That's the Earth energy balance. So tell us how you used that information to also come up with climate sensitivity.
Yeah, that's really remarkable data measured by NASA satellite, the Ceres instrument. Clouds and Earth Radiant Energy System is what the acronym stands for. But you can measure the changes in the solar energy reflected by the planet and the thermal heat energy emitted by the planet. You can measure those very precisely. Now, you can't calibrate them absolutely, but we can get the absolute calibration from measurements over a decade or longer with the Argo float data. These several thousand floats are distributed around the world ocean. They're deep diving floats, which dive to a depth of 2 kilometers and then resurface and radio their measurements to a satellite. And so we can measure the changes in the heat content of the ocean. And that's where the energy imbalance of the planet, where the excess energy must go, is into the ocean. And so that allows a calibration of this Earth's energy imbalance. And one thing we learn is that Earth's energy imbalance has doubled in the last decade compared to the prior decade. And so that's, of course, consistent with the global warming acceleration, because the ultimate drive for the warming is the planet's energy imbalance. If you've got twice as big an imbalance, you should expect the warming to accelerate. But the other thing is, if you just look at the solar reflection, the reflected solar energy, Earth has become noticeably darker during the period of satellite data, which began in year 2000. The darkening is now 0.5%. The albedo of the Earth, which is about of the order of 29%, has decreased by 0.5%, which is a big deal. That's equivalent to 2 watts per meter squared. So it's becoming dark, it has to be becoming darker mainly because of cloud changes. We can see, that the surface is.
By the way, I should tell. So when it gets darker, it absorbs more energy from the sun, and if it's lighter, the albedo is how much it reflects sun away. So as it gets darker, and these numbers are not, you say 2 watts. I mean, as you and I once did a calculation, this is measured sort of in the range of 1 million Hiroshima-sized atomic bombs going off on the Earth every single day. So the amount of extra energy absorbed from the sun from this darkening is not a tiny bit. It's a crazily large number.
Well, yeah, and the more relevant comparison is to, is to the 4 watts that causes the global warming of, now we estimate 4.5 degrees Celsius at equilibrium. So 2 watts is a big deal. Now that's not a forcing. We would like to know what composes that 2 watts per meter squared. We know the surface of the planet itself has become a bit darker because the area of sea ice has decreased. But that we can see exactly where that's occurring and see how much it's contributing to this 2 watts. And it's about 0.15. A fraction of a watt. So most of it is a change of albedo due to cloud changes. That's the only thing that's left. Aerosols themselves uh, have become less, but their effect is less than 1/10 of a watt, the direct effect. So it's mostly cloud changes. And but that itself could be partly aerosol forcing. Aerosols, I mentioned that their forcing is estimated to be between -1 and -2 watts per meter squared, but that's mostly from their effect on clouds. They're
Right. They form the nuclei for clouds. They make clouds last longer, be brighter. And so it's not the aerosols themselves reflecting the sun very much. It's their impact on clouds that reflect the sun.
Yes. But we had estimated in our first of our long papers that forcing that could be as large as 1/2 a watt per meter squared. The people who try to model that with the aerosol cloud microphysics get a smaller number, closer to 1/10 of a watt per meter squared. But even if it's as large as we estimated, that still leaves more than 1 watt per meter squared for cloud feedback. And that is, of course, consistent with large climate sensitivity. If climate sensitivity were only 2.5 to 3 degrees, there would be almost no cloud feedback. But this is telling us that, in fact, cloud feedback is large. And that is another way to come to this conclusion that climate sensitivity is large.
And we had George Salutis on the program once talking about his study showing how we're getting decreasing clouds in certain places due to the warming, and that's a big climate feedback. So yeah. So there's
George's point is that the question is, how does that cloud feedback work? And George Salutis argues that it's largely a shifting of climate zones, right, which is causing the cloud change. But whether it's cloud microphysics, it's probably some combination of changes in the cloud microphysics and the shifting of cloud zones. But doesn't affect this conclusion that clouds are an amplifying feedback and climate sensitivity is large.
So let's see. We summarized so far. We talked about paleoclimate data and how that showed we got about a 4.5 degree climate sensitivity. Now you just spoke about how you look at satellite measurements such as the dimming of the Earth, and when you work out the numbers, you get in that 4.5 degree range. And you said you also use global climate models, or GCMs, to figure this out as well. Can you tell us how you use GCMs to calculate climate sensitivity?
Yeah, and in fact, we use what we call the climate response function. You know, I showed in 2008, I had a privilege of giving the Birkness lecture at the annual meeting of the American Geophysical Union. And I showed that you can reproduce the GCM simulations of global temperature change very well with a very simple calculation. And that is, if you know the response function of the model, if you run your model with a standard forcing, in particular, let's say you double the amount of CO2 and just let the model give you the computed temperature change as a function of time. That's the response function. You can then, it turns out, and I showed in that talk, that you get essentially the same global temperature change from the response function as you do from running for any given scenario of climate forcings, any transient scenario that you like. And just use the response function, and you can calculate how the global temperature would change without rerunning your GCM for every different forcing scenario. So anyway, we did this in our second paper, the second long paper, and showed that if you want to match the observed temperature change, especially during the period while the planet was warming very rapidly, which began in 1970. Because that was by 1970, the rate of addition of greenhouse gases had become very large. It was going up at a rate of about 0.45 watts per meter squared per decade. So that's a very strong growth rate for greenhouse gases. And in the IPCC best estimate for aerosol forcing, they have the aerosols as being constant, practically constant from 1970 to 2005. That's the period when global temperature was rising linearly at a rate of about 0.2 degrees per decade, or 0.18 to be exact. And what if you want to match that and you're keeping the aerosols constant, then you need a climate sensitivity of 3 degrees Celsius for doubled CO2.
IPCC shows, right?
Well, that's what we show in our modeling in the second paper. However, we argue that aerosol forcing was probably still increasing during that period. The global average sulfur emissions, and sulfate emissions are the largest source of atmospheric aerosols, and sulfur is a constituent of coal burning. So that had leveled out between 1970 and 2005. The global average sulfur emissions remained pretty constant. And that's in part, it seems to be why IPCC is estimating that the aerosol forcing was constant. We show a graph at the end of our second paper comparing the sulfur emissions and the IPCC forcing, and they're almost congruent. But what is actually happening during that period is emissions are decreasing in the United States and Europe, but they're increasing in East Asia.
Like in China.
And they're increasing over the ocean as the amount of ship traffic increased substantially over that 35-year period. So what you're doing is spreading the same amount of sulfur emissions, but you're spreading it over a bigger area, including more of it over the ocean. And the effect of the aerosols is highly nonlinear. If you pump aerosols into air that's already polluted, it doesn't have much effect on cloud formation. But if you're spreading this over a bigger global area, then you're still having more effect on clouds. And we looked at, there are some efforts to model that. And in particular, I think that Suzanne Bowers and her colleagues have some of the more advanced efforts at that modeling. And she had two different models, one of which concluded that aerosol forcing increased by 0.5 watt per meter squared over that 35-year period. And another one, which was a cruder, older aerosol model, got actually an increase of -1 watt per meter squared. So we looked at, using this climate response function to replace the need for GCM modeling, we looked at those three different scenarios. One consistent with IPCC, in which the aerosol forcing was constant, and one in which the aerosol forcing increased 0.5 watt, and one in which it increased 1 watt. The constant one requires a climate sensitivity of 3 degrees to match observed global warming.
Mm-hmm.
One with 0.5 watt increase in the aerosol forcing required 4.5 degrees.
Right.
And the one with a full watt increase in aerosols would require a 6-degree sensitivity. Well, we can also use those models and look at the whole period from 1850 to 2024, and the one that fits the whole period best is the intermediate one, the 4.5.
4.5.
So it's another way we come to the same conclusion that we get from the other two approaches, that climate sensitivity is a lot higher than IPCC's best estimate.
So you came up 3 different ways, and now you're working on something new. Is that right? Can you tell us what you're working on now, and when you plan maybe to release that?
Yeah, it's actually it's surprised me. I'm revising my draft of the book Sophie's Planet, and chapter 10, which was the one on Venus. I actually now changed the title of that chapter to the Venus Syndrome.
Okay.
For decades we've been saying, oh, it's useful to look at the planets, to look at the range of planets, and that tells us something about the greenhouse effect, and we see, for example, that on Mars it's got a small amount of greenhouse gases, and it's got a greenhouse effect of 5 degrees. It's 5 degrees warmer than it would be without its atmosphere. On the Earth is 33 degrees Celsius warmer than it would be without an atmosphere. And Venus is about 500 degrees warmer. And so that gives you this, the Goldilocks planets. But what we can show now is we can learn actually a lot more, and from this planetary comparison, using a simplified GCM, which the physics has been reduced to its core, so that you can actually run the model all the way from ice ball Earth to the Venus Syndrome. So I will send this out within about a week.
Okay.
And it gives us a fourth perspective. And again, it turns out to be consistent with the other 3. And it gives us some additional insight. So I think you'll find it interesting, but I won't talk about it more now, but I'll send it out.
I'm looking forward to that.
Yeah,
it'll be really very soon. So you had these 3 ways; they were all consistent, showing 4.5 degrees, and now you're working even on a 4th one that might bring them all together. But let's talk about some other things here. First of all, you were supposed to, maybe it's related, but you were supposed to be on this program about half a year ago, or maybe more actually, but you continually delayed that, and you came on now. Why did you come on now?
Well, yeah. Well, I think we should confess, Dan, that the reason you're able to finally twist my arm is because you helped me get funding to keep my organization alive this year.
Okay.
And by the way, this last week we were able to put out the advertisements for 2 entry-level positions. Makiko Sato, who has been our longtime expert on climate data, and has done such a great job because she's
incredible graphs and things that many people have seen. They might not know it's from her, but
yeah, she's very artistic, and she's also just very dedicated. So she would keep updating our different data sets. But anyway, she's finally retired, and she was our most senior scientist, had been working with us several decades. So I can use, since with your help, I'm able, my long-term supporters are becoming reluctant to continue support for our organization, which may be related to our bad reviews in the media, but it's hard for philanthropists to determine whether or not someone the merits of their work. Anyway, but fortunately, we have a level of funding comparable to what we had the preceding year, so I can support 2 entry level. That by that I mean like a master's degree level position for a data person and for a program coordinator. And we've been without a program coordinator, and I've been without administrative assistants for the last few years. But now with these 2 positions, I think we can be much more effective. And also because, as I mentioned in one of my recent communications, we've moved back to the city, to Columbia University apartment. And so I have more time. I don't waste time commuting and having to do work outside. So I'm really, so now I'm going to finish Sophie's Planet.
Okay.
I had finished the draft of 47 of the 50 chapters when I discovered Jessica Tierney's paper and the paper on the groundwater, which made me realize, we finally have the information to do a better job on climate sensitivity. And it changes the story. It makes it more accurate. And so I had to, but it took like 3 years to do these 2 long papers.
Well, by the way, we're going to get into like the implications of this in just a couple questions from now on the implications of this higher climate sensitivity, which is ground shaking, I think, climate research from my perspective. It's really super important. But before we do that, I have another sort of more general question for you. Are you willing to come back at some other time and talk about the policy implications of the climate science you're working on?
Yeah, but I want to still be I don't, if I don't finish Sophie's Planet now, either Anik, my wife, or your sister Nancy is going to kill me.
I should mention my sister is the editor for the publishing company that's publishing Sophie's Planet. Yeah.
Nancy Miller was the editor for my first book,
Storms of My Grandchildren. Yeah.
And she will, I hope, be the editor for Sophie's Planet. And so that's got to be my priority.
But once you get that done, and maybe we'll take little bits of your time away to talk about this and so to communicate with the public here. So I wonder.
So
go ahead.
Yeah. Well, I have to make the broader story clear in that book, because the situation that we're in now, most of the discussion is from, on the one side of the spectrum, we have the people who are very concerned about climate change, but there's a narrative that goes with that. And on the other side, we have, you have the most extreme people who just deny the reality of climate change. But you also have
the government now, but okay.
Yeah, but we also have people who believe that you can address the climate change with technology, and the climate issue may be exaggerated.
Yeah.
So, and you have to, so I listen to both of those. A lot of my friends are on the extreme left, but
Okay.
uh, I, 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 I subscribe to people on both sides so that I can understand the
Sure.
perspectives from both sides. And as scientists, you have to do it that way. And I have always been a political independent because
Right.
you don't want your science to be affected by your political position. So it's much better, I think, to be in the center and objective, open-minded to the science, and not have your opinion influenced by political position.
Okay.
And so it's hard. It took me a long time to realize just how much that can affect things. Let me just give you one example. Um, and it's one that which you will understand very well because you've actually collaborated with me on trying to educate people and policymakers about the merits of a simple carbon fee.
That's right.
If we don't make fossil fuels include their cost to society, it's very hard to solve the climate problem.
Hmm.
Uh, and therefore, way back in 2006 or 2007, I started arguing for this carbon fee and dividend, in which you have a gradually increasing price on carbon, collecting the money from the fossil fuel companies at the mines or the ports of entry. So it's very simple to collect it and then distribute it in a simple way to the public.
Okay.
Uh, if you give an equal amount to everybody, then 70% of the people, the low income people and
Okay.
most of the middle income people will come out ahead. Uh, but
So,
but we couldn't. But now for me to get to the point, I wrote an op-ed for the New York Times, which was called "Sack Goldman Sachs," and it was because the proposed climate policy was cap and trade with offsets, which
hmm
is designed by big banks like Goldman Sachs and is preferred by the fossil fuel industry. And it's
Sure.
basically it's a half-assed way which will not be effective in the long run. It will do a little bit of good, but mainly it enriches the banks, those who are skilled in trading.
So Jim,
But
I'm going to put in the description, the paper you and I wrote that goes into that. And I'll also, by the way, getting back to something you said
well,
previously, I'll
but
add a
my
link to make people can make donations to the
yeah, but
Columbia
no, but
program.
let me get to the point on
Mhm.
on the
Okay.
media and the communications, and that is, so I submitted this op-ed. Well, what happened? They changed the New York Times changed the title to "Cap and Fade." Could totally change the meaning of my op-ed, and
Mhm.
at the same time that my op-ed was published, there were two side-by-side articles by Paul Krugman. One of
Mhm.
them was started with the first sentence was, if there's any climate policy, it's going to be cap and trade,
Right.
period. That was the first sentence in the article. And he also, in addition to these two articles by Krugman, there was uh, his blog came out at the same morning as my op-ed, and it was titled "Unhelpful Hansen," and explained why that a fee and dividend didn't make sense. And it was then there were like 500 more than 500 responses to Krugman's article. One of them and some of them by economists, most of whom seem to agree with my position. But one of them in particular said, Krugman is Colonel Nicholson. If you read the book Bridge Over the River Kwai, Colonel Nicholson was somebody who actually didn't realize that he was working for the enemy. He was helping the Japanese construct a bridge over the river, and they were sending their military equipment. Well, at the last moment, of course, in the movie,
they blew
up the bridge.
Right.
But
so in our paper, which I'll link, we show that cap and trade actually turns out to be the worst way to do carbon. Well, maybe not the very worst way, but
it's very ineffective, it enriches the people that are already rich. Well, fee and dividend it helps out in the current wealth disparity that we have in our country and many other countries. But my point is, so then here later, sometime later, Krugman is allowed to publish every couple of weeks, or was allowed when he was still active. And here, my biographer, Mark Bowen, who's a good physicist, he writes on his blog, "Oh, now I understand." After reading Krugman, he said, "Now I understand that Hansen's fee and dividend doesn't make sense." So, if you have the control of the media, it's just very hard. And the New York Times goes along with the
Krugman side.
the narrative that is attached to the narrative on climate change, and it's very hard to change that. And that's just one example that's going to be in my book.
Jim, I want to get back to.
I have to get.
I want to get back to some of the impacts here, and I did promise you I would let you off in exactly 1 hour, but your answers went a little longer than I thought. Can we have a little more time to finish up these questions?
Yeah, it depends. As I said, remember, when I agreed to come on, I said I don't want to talk about
not politics. You were just doing that, but Okay. I want to turn the question over to Stacy. I'm going to bring Stacy, and she has a question. Then Eli, and then Leon has a question, and then we'll see how it goes there. Oh, wait, let's make Jim the big guy there. Okay. Welcome, Stacy, and welcome to your new place, wherever that is there. You just moved in.
I am in Oakland now. So,
very good.
Just yesterday. So, anyway, it's so good to have you back here, Jim. And I can't help, and I'm actually launching both of my kids off to one back to and one starting college today. And you are a devoted husband, and your wife is on you to finish your book, and father and grandfather. Sophie's Planet. You're doing all this. You are thinking about young people, and we all have our kids and people that we care about. What would you say to young people when it seems like we just keep dooming them to Venus with our actions?
Yeah. So the whole purpose of Sophie's Planet, I want to try to communicate with young people. They don't understand the power that they have. And when I started talking about fee and dividend in 2007 or so, what happened in 2006 was that I revealed that NASA, at the request of the White House, had stopped me from speaking to the media. And I let them do that for a while until I had collected the evidence of what they were doing and substituting other people when the media wanted to talk to me. So that got a got a lot of attention, including on 60 Minutes and the front page of the New York Times. So then I was asked to speak to universities. And when I went to these universities in 2008, all the young people were coming out in support of Barack Obama. And when Hillary Clinton was the preferred candidate of the Democratic establishment, but it was mainly because of all this support of the youth that Obama overcame her and got the nomination. And he spoke about a planet in peril, and they just assumed that the problem would be dealt with. But in fact, although I had tears in my eyes when he was elected on election night, because it was amazing. Partly because our country could actually elect a black person.
Yeah.
That was part of the story. But also, he was a climate person. But he was already part of the elite. So he's picked a science advisor from Harvard. He let the banks off the hook. He took the advice of the big banks he had the opportunity, because of the financial crisis of 2008. He could have introduced a carbon fee and dividend. And I tried to get the science advisor I wrote a letter. He would not deliver it to Obama. It was addressed to Obama, but the science advisor wouldn't deliver it because he was telling Obama everything. Anyway, so we basically missed the opportunity. And again, in 2016, young people amazingly almost pushed Bernie Sanders above Hillary, again, the establishment's candidate. So they have tremendous power. And you should look at the preface to Sophie's Planet. I put a draft of it up on my website a few weeks ago, and I got some useful comments. So I'm going to put up a revised draft, which is even better, I think. But anyway, the bottom line of it is our democracy is threatened by the role of money.
That's right.
If we can't get money, it's both the military industrial complex, the fossil fuel industry, and then there are others, smaller ones like pharmaceutical industry. All of this is determining our government policies. And both political parties are taking money from these special interests. If we can't overcome that problem, it will be very difficult to solve the climate problem. But we could overcome it. And that's why I'm going to start, one of the reasons I come back to live in the city, I'm going to start talking on campuses and trying to persuade this Generation Z that they have the power to change the system. We're past the time when we need what our founders said was a revolution. You'll need them occasionally to take care of graft, and it is graft. We even have our Congress people are actually allowing themselves to trade in stocks, which they influence the value. It is crazy, and that has to be fixed. So that we have to start, and it's an awful lot to expect college-age kids to understand the big picture, but I think they can do it, and so that's what we have to do. It's anyway. So I got to finish.
Thank you. So thanks, Stacy, and. Jim, I got you over there. I want to follow up with a question on the implications of everything we were just speaking about earlier, and that you said previously that we're currently at 1.5 degrees Celsius of warming for all practical purposes, though some scientists are saying we can still stay under 2C of warming if we would just start lowering fossil fuel emissions. But what are your thoughts on 2C of warming, including when we might reach it, and what are the possible impacts of accelerated warming that we should be concerned about?
Okay, well, we're at 1.5 degrees now, averaged over El Nino and La Nina cycle. And global temperature had been going up 0.18 degrees Celsius before the acceleration. Now, with this accelerated warming, which is going to continue at least a little longer, it's more like 0.3 degrees. So that would tell you that in 15 years, we will reach 2 degrees. That's 2040. And now, one of the things that's interesting about the climate response function, which is the global average response to a forcing, is that you get a lot of the response in just the first decade, 10 to 15 years. So if we do make a change in the forcing, we can alter that expectations. But it's very hard to do that because of it's hard to change the rate of global temperature change because of the inertia of the system and the inertia of the energy system. We're adding renewable energies quite rapidly, but we're not reducing. That they're on top. They're added on top of the fossil fuel emissions. They're not really reducing that. So the answer is it's probably going to be close to 2040 that we hit.
Now, is 2C, quote, it's like a target for many of these international program, Paris Accord. Is it safe? Would you call it safe temperature, or is it something that we really should be quite concerned about hitting 2 degrees?
That's another interesting story, and I will have an interesting bit in the book about our paper, which was titled "Ice Melt, Sea Level Rise, and Superstorms," and the subtitle was 2 degrees Celsius is highly dangerous. Okay. Now that paper got a great review by one well-known scientist who said it had brilliant insights, etc. But the other referee was an IPCC lead author who was determined that the paper not even be published. Well, the journal then, the editor actually was very favorable about the paper, and they got 2 more referees, both of whom agreed it was an important paper that should be published. And then the editorial board got involved, and they said, I have to change the title. And I argued with them that, well, if a person looked down the street late at night and saw people loitering, guys loitering, and one of them slapping something that looks like a blackjack against his leg at a dark street, would you consider that street dangerous and decide to take a different route home? And so then the editor dealing with me was very distressed by what the editorial board told him. They said that I could not even include that argument in my letter to them. Mm-hmm. They said, you have to change the title or we won't publish it. And I cannot include that argument in my correspondence. And the thing is that the journal was using this publication procedure where it's all very open. The reviews are all published, the responses are published, the public comments are published, but yet my letter cannot.
So it was changed, but could be dangerous. But so the answer is that it is dangerous. Can you just tell us some things to worry about? And I know you've written about very large amount of sea level rise, even possibly later this century, and AMOC collapse. Are those 2 things that concern you?
Yeah. So this you know the big issues are AMOC
The Atlantic
and sea level
meridional
rise.
overturning circulation, or the ocean conveyor belt bringing heat from the tropics to northern Europe. That's the AMOC, and it could
Yeah.
shut down.
Yeah.
Right.
Yeah. And my our conclusion is that those are both likely to happen if we stay on this path that we're on. You know, but this is a complicated scientific story. At the time we wrote the paper, in the period 2005 to 2015, the mass loss from Greenland and Antarctica, precisely measured by the gravity satellite, had doubled in 10 years. And in our paper, we looked at what the consequences would be if that doubling continued with a 10-year time scale, or if it continued with a 20-year doubling time. And that would lead to meter scale sea level rise on time scales of 50 to 150 years.
Incredible amount of
that
sea
range.
level rise.
Now, what's actually happened in the last 10 years is snowfall especially over Antarctica, has started to increase a lot. So if you just look at the mass balance of the Antarctic ice sheet, it's actually started growing
In Antarctica.
some years. Yeah, in Antarctica. But that's because the atmosphere now holds more water vapor, so it snows. But at the same time, it's the feet of the ice sheet that are important. The ice shelves that come out into the ocean and extend down the continent to a depth of a couple of kilometers in the ocean. And and the ocean is getting warmer. So those are going to melt faster. But on the short time scale, in 2016, there was a sudden change in the ocean circulation around Antarctica, which allowed the deepwater formation to at least temporarily increase again. So it's a complicated story. You have to, but on decadal timescales and longer timescales, the warmer ocean is going to cause the ice melting to increase, and we're going to get more ice pouring into the ocean, and so we have to do something.
So we still have to worry. Maybe is it still possible to have several meters of sea level rise in the next 100 years? You think that's still a possibility?
Yeah, absolutely.
Like 10 feet of sea level rise.
So, one of the reasons I retired from NASA was I wanted to be free to do this stuff without the bureaucratic time that I have to spend with the bureaucracy. And when Trump was elected the first time, there was an opportunity. There were philanthropists who were worried that the climate research is going to be terminated. And so there was an opportunity for announcement of opportunity. And I proposed with some of the best scientists in the world, in my opinion, for a 5-year grant of $1.5 million per year to really try to understand this problem that we're talking about: the ocean circulation, the ice sheet response, the global sea level, the overturning ocean circulation. And it requires this same approach where you use paleoclimate, you use the GCM modeling, and you look at what's happening today in the ocean and with energy balance and all these things. Well, we didn't make it, and I feel I may be paranoid, but I feel that the IPCC scientists who have been given too much power to control the agenda and the narrative for climate change. So that's as soon as I finish Sophie's Planet, I'm going to try again to get a research program going on this, because those are the fundamental issues. And
so the next question comes from Eli, who has a question, kind of a follow-up. You mentioned all these potentially very major impacts, and his question's about what we can do about it. So Eli, welcome. What's your question for Jim?
Thanks, Dan. You've previously outlined steps to limit climate impacts that we can take in addition to reducing fossil fuel emissions. What are your thoughts on carbon dioxide removal, taking CO2 out of the atmosphere, and on sunlight reflection methods, also known as solar geoengineering?
Yeah, I'm going to go to a meeting in Finland organized by this young people who they're concerned, even though they live in a cold country, but they're concerned about the rapid changes that they're beginning to see, and want to investigate whether there are actions that would make sense to try to affect the planet's energy balance. Well, before you can answer that question, you need to have some progress in understanding the issues that we were just talking about the ocean and the ice sheets. So I want to be circumspect about that at the moment. That was what I told Dan. I didn't want to talk about that stuff right now. That's policy. That's a policy which I think, of course, you would like to be able to take CO2 out of the atmosphere. Nature is actually helping us. One of the CO2 increase now is only half of the CO2 emissions. So the system is actually taking up CO2 faster than was expected. 20 years ago, it was taking up 40%. And even though our emissions have grown a lot, and the predictions were that this uptake fraction would decrease, in fact, the uptake fraction has increased. So there may be ways that you can encourage that increase to be the uptake to be even larger. And I've been involved as a co-author on some of the papers with regard to enhanced weathering. Fertilize your fields with rock dust to get them to take up CO2 more effectively, and even with Sophie, my oldest grandchild, we distributed 1 ton of biochar on our farm to improve the health of some trees that recently planted trees that were not doing so well. So there are things you can do to remove carbon dioxide from the atmosphere that make good sense for other reasons. I think doing it doesn't seem economically sensible yet. We haven't found a way to extract it from the air. You could make liquid fuels. If you could extract it from the air and make liquid fuels with it and use those fuels instead of fossil fuels, that would make sense. But as yet, those methods are not economically competitive with fossil fuels. Until you get a carbon price, they're probably not going to be.
And any comments on solar geoengineering? You've been one of the few climate scientists who said it might be something we need.
Yeah, well, we're not at the point of recommending that. The focus should be on price on carbon. that's the way you could drive down emissions rapidly and get the natural system to help you draw CO2 out of the atmosphere, and you can help the natural system. But so as I said, I want to be circumspect about that at the
That's
moment.
good. Hey, we're gonna bring in Leon Simmons, one of your co-authors on the global warming, the pipeline paper. He has a question for you, going a little bit farther back than we've been talking so far.
Hi, Jim. Great to see you on Climate Chat. Yeah, I wanted to ask you to talk a bit about. Wait, let me do it like that. Yeah.
Yeah.
Let me. Sorry. I wanted to ask you to talk a bit about the impact of human emissions before the Industrial Revolution. As we wrote in Global Warming in the Pipeline, there's about a half a watt per square meter greenhouse gas forcing increase from about 6,000 years ago until 1750, the start of the Industrial Revolution. But there was global, at least no global warming, and some indicators say that there was even global cooling, especially over the Northern Hemisphere over that period. And that's called the Holocene temperature conundrum. And of course, in the paper, we explained that this could be also explained by an increase in anthropogenic aerosol emissions, so more burning of biomass by people starting agriculture and deforestation around the world. So my question to you is, what could this contribute, these two competing greenhouse gas and aerosol forcings from the pre-industrial era? How could that impact the future climate change over the next decades and century?
Yeah. So, well, you've summarized nicely that there was a puzzle as to why the planet was, if anything, cooling off during the last 6,000 years, because CO2 and methane were increasing during that period, and a lot. I mean, half a watt, this should have been global warming. But if anything, there was either neutral or slight cooling of the planet during that period. And no other good explanation has been proposed other than, well, humans are also producing aerosols because they were using forests, deforesting parts of the planet and using that for fuel. And when you put the aerosols from this fire burning into the atmosphere, into a otherwise pristine atmosphere, it could make the cooling effect. So probably that is the case. And of course, that fire burning, the burning of wood, sticks, is continuing. We pointed out the references even in Europe and in the US more so. There are people who still burn wood for heat in the winter, especially. And globally, biofuels have not decreased, so there's probably at least half a watt of negative forcing, aerosol cooling from wood burning, from biomass burning, from biofuel burning. And that, so that's not included in IPCC. IPCC has zero aerosol forcing at the start of
That's the baseline
scenario. So there's that additional forcing. As long as that doesn't change, then it doesn't affect the interpretations of what's happened over the last century. But eventually, you would think we will move to clean energies because the health consequences of that biomass burning is enormous. Several million people a year die of indoor air pollution.
Yes, many women and children.
So, Yeah. So that's an additional reason why we have to understand the aerosol part of the problem.
Okay. So, Jim, thank you for that. And thank you for the whole session here. Is there any final words you have for our audience before we wrap up?
I know, sorry that I'm so long-winded. It took longer than we
It did.
thought. Sorry.
But
Yeah. But thanks for your
yeah, sure.
support,
And
Dan.
I want to thank you
And,
for coming on Climate Chat, and thank you for all the work you've done,
sure.
not only to advance climate science, but to inform the public about the challenges we face. And I want to thank everyone listening. If you've appreciated the program, please like and subscribe and comment below so this important message can reach more people. We will add some links about the fee and dividend that you mentioned and a link to donate to your program so that if the public wants to help you with what you're doing, they'll be able to. So, Jim, thanks for coming, and thanks to everyone for listening.
Thanks, Dan.
And we will see
right.
you next time.
Bye-bye.